Welcome to Lecture 2.2, Linear Independence and the Wronskian. Let me pose a question that will serve as a motivation for the main topic of this lecture. To solve an nth order linear homogeneous ODE, we need to somehow find n linearly independent solutions. In other words, a basis for the solution space. Recall this is a vector space of dimension n. Here's the question. Suppose we have n functions that we know are solutions. It's easy to check that. But how can we determine if they are actually linearly independent or not? The case when n equals 1 is easy. A single function, y1, is linearly independent if and only if it is non-zero. Recall we've been over this before. The case when n equals 2 is also not difficult, but we have to be careful, and I'll explain why in a moment. First of all, note that what is true is that two functions, or a set of functions, y1 and y2, is linearly independent if and only if one of them is not a scalar multiple of the other. So this is best seen geometrically. A two-dimensional vector space looks like a plane, so if we have two vectors or functions, y1, y2, those things determine a plane if and only if they are not collinear. So there's an example of it. A non-example is if these things lie in the same line, say this is y1 and this is y2, then the vector space that they span is just going to be one-dimensional, or a single line. Now, even though this case is easy, these are linearly independent if and only if one is not a scalar multiple of the other, I did say you have to be careful, and let's see why that is. So I'll answer that question with a question. Are the following functions linearly independent? Sine of 2t and sine of t cosine of t. Now it looks like at first glance that they aren't, but if you remember your double angle formulas, recall that the sine of 2 times theta equals 2 times the sine of theta times the cosine of theta. So what that means is that if you have 1 times the sine of 2t plus negative 2 times the sine of t cosine of t, then you get 0. So here is a nonlinear combination of these two functions, y1 and y2. In other words, 1 times y1 plus negative 2 times y2 equals 0, so they cannot be linearly independent after all. Not surprisingly, things can get much more complicated if n is greater than 2. We don't have a simple condition like this at all. For example, let me ask you the following question. Are the following functions, y1 is e to the 2t, y2 is e to the minus 2t, and y3 equals cosh of 2t, are these guys linearly independent? And the answer is no, they actually are not. And recall that cosh of 2t is 1/2 e to the 2t plus 1/2 e to the minus 2t. So if you see it like this, now you can say, oh, okay, these things cannot be linearly independent because this guy is 1/2 of y1 plus 1/2 of y2. In other words, if you take 1/2 of y1 plus 1/2 of y2 plus negative 1 of y3, you get 0. So this is a non-trivial linear combination of these guys, which is 0. Not clear just by inspection. Here's a harder question. What about the following three functions? y1 is e to the 2t minus 5e to the minus 2t. y2 is 3e to the minus 2t minus cosh of 2t. And y3 is e to the 2t plus e to the minus 2t plus cosh of 2t. So is there a linear combination of these functions? In other words, c1 y1 plus c2 y2 plus c3 y3 that is equal to 0? Well, if there is one, it's certainly not clear how to construct it because it's going to be, you got to do some math. You could maybe, if there is one, search for it and find it. But if there isn't one, then you might be searching for a long time, and if you don't find one, it's not clear if it's because there isn't one or because you just didn't find it. So yes, there are actually algorithmic ways to do this. If you take a linear algebra class, you will learn about them. But I claim that we actually know the answer to this very easily without actually computing anything. So the answer, I claim, is no. These things are not linearly independent. And why is that? Well, all three of these functions, e to the original ones, e to the 2t, e to the minus 2t, and cosh of 2t, satisfy or solutions to the following differential equation. Y double prime equals 4e to the 2t. You can check this if you want, but it's not hard to check that all three of these functions are solutions to this. Now you know that the general solution to this equation is a two-dimensional vector space. That means that y of t equals c1 y1 of t plus c2 y2 of t. Now, in any two-dimensional vector space, so this is two-dimensional, in any two-dimensional vector space, think about like a plane in R3. That's the easiest thing to picture. If you have a plane in R3 and you have any three vectors on the plane, doesn't matter, any three, those vectors are going to be linearly dependent. Similarly, all three of these functions are solutions to this ODE, and the solution space is a two-dimensional vector space. Whatever you want to call them. I said y1 and y2. I guess I don't necessarily mean this y1 and y2, though actually, in fact, I could, because these are linearly independent solutions. They form a basis for the solution space, so there's no way that three of these functions can be linearly independent in a two-dimensional vector space. Here's a definition of an object that we call the Wronskian. This is very commonly taught in an intro ODEs course. I usually don't actually include it because if you don't understand the linear algebra, it's this random thing that you memorize without any sort of motivation. And it's usually not needed because in an intro ODEs course, you usually only solve first and second order ODEs, so it's pretty clear when two functions are independent. First order, well, it has to be non-zero, and second order, one can't be a scalar of the other. But let's introduce this now. I think we have enough mathematical maturity to appreciate it, and we will give some applications of how it's useful in the remainder of this lecture. So let's suppose that we have n functions. Let's call them, I call them f1 up to fn, and these are, they don't have to be defined on the whole real line. Maybe they're like log, so they're not defined for negative numbers, but suppose they're defined on an interval. Let's call that alpha and beta. The Wronskian of these functions, this is defined as follows. So it's a function of x, but it's defined by these n functions, and it's defined as the determinant. This is an n by n matrix, and it's the determinant. Basically, in the first row, you put all the functions, f1 up to fn, and then you take the successive derivatives of these and you make the columns where the columns are the derivatives of each function. So now what good does this do? This is a nice object, but I claim that this actually tells us something about whether these n functions are linearly independent or not. Before we say anything more about the Wronskian, let's compute a simple example, just so we get the feel as to what's going on. So here are two functions, cosine of t and sine of t. I hope you agree that these are indeed linearly independent. So the Wronskian of y1 and y2 is, well, let's put the functions in the top row, cosine of t and sine of t, and then let's put their derivatives below them. This is minus sine of t, and this is cosine of t. And the determinants, so it's cosine times cosine minus sine times negative sine. So that's cosine squared of t plus sine squared of t, which equals 1. Now, here's the main theorem. It's very simple. If the Wronskian of n functions is not identically the zero function, then this set of functions is linearly independent. So in this example above, the Wronskian of cosine and sine was 1. That's not the zero function. So therefore, these functions are indeed linearly independent. Now, here's the bad news. If we compute the Wronskian, and it happens to be equal to the zero function, then that does not necessarily imply that these functions were linearly independent to begin with. It provides evidence that there's a very good chance that they are, but we can construct examples of functions that are linearly independent and whose Wronskian is zero. Here's an example. Let's take two functions, f1 being x squared and f2 being the absolute value of x times x squared. Now, what's the difference between these two? Well, so x squared has to be non-negative, and this guy can be negative when x is less than 0. This is essentially x squared, except when we're less than 0, it's negative. So for example, here's what y1 looks like. You all know what x squared looks like. So this is y1. And then y2, well, it's x, again, these things are the same when x is positive, but if this is negative, then we reflect it here. And so think of it as like a parabola, but it's broken into two pieces and put together. Now, it's not obvious at all, but this function here is actually smooth. It's differentiable, and the derivatives are continuous. So we can take derivatives of f2, and if we do that and we compute the Wronskian, we get that f1 and f1 prime, f2 and f2 prime. I'm not going to do it because we haven't studied the derivatives of functions like this, and personally I've never actually done that myself. I don't even know how to do it. I could probably figure it out, but I believe that I've heard repeatedly, it's a classic example that the Wronskian of this is equal to the zero function. However, these guys are not linearly independent. It's very clear that this guy y1 is certainly not a scalar multiple of y2. I'm going to spend much of the rest of the lecture giving you applications of the Wronskian and convincing you why it is indeed useful. So one of these is Abel's theorem. So this says that if we have two solutions, y1 and y2, to a second order homogeneous ODE, so y double prime plus a of t y prime plus b of t y equals 0, when a and b, these are continuous functions in an interval, let's say alpha to beta, then the Wronskian of these two solutions is given by the following formula: c e to the minus integral of a of t dt, where c is some constant. Now, this is remarkable for several reasons. First of all, a minor point is that it does not involve b of t at all. But most importantly, we don't even have to know what these solutions are. Suppose we can't even solve this ODE, but we can still figure out what the Wronskian is. It's given by this formula. Here's another important observation. Since this exponential function is positive, exponential functions cannot be negative or 0, then the Wronskian is either identically 0, that happens if this constant c is equal to 0, or it's never 0 on the interval a or alpha to beta, where this ODE is defined. Let's take a few minutes to prove Abel's theorem. It's actually very straightforward, and I think seeing it, you'll understand why it's true, and both why the Wronskian is this simple formula and why that formula is either identically 0 or never 0. So the crux of the proof is the following straightforward claim that the Wronskian, this is a function of t, is a solution to the following first order linear inhomogeneous ODE: w prime plus a of tw equals 0. Now this is something we can solve using separation of variables, and we will get, in fact, this formula right here from it. Okay, so let's verify this. Let's first write out what the Wronskian is. It's this determinant, y1 prime down the first column, and y2 prime down the second column. So we take the cross product of this, so, well, I guess this product minus that product, that's what I'm calling cross product. So that's y1, y2 prime minus y1 prime, y2. So that is the Wronskian, and we need to show that this verifies this or satisfies this ODE. So we need to take the derivative. That's something we can do using the product rule. Each of these terms is a product of two functions of t. So let's do that for the first term, and that's y1 prime, y2 prime, plus y1, y2 double prime. And now this second term, this is negative, so let's say this is minus y1 double prime, y2, minus y1 prime, y2 prime. Now notice right away that this first term cancels out with that second term, and so we are left with these middle two terms, y prime, or as w prime, I mean. And now we want to plug both of these into this ODE. So w prime, that is just y1, y2 double prime minus y1 double prime, y2, and plus a of t w. This is plus a of t, and then w is up here. That's y1, y2 prime minus y1 prime, y2. And now we need to show that this is indeed 0. So how are we going to do that? Well, there's y1s in here and there's y2s in here. So let's write them out separately. So this is y1 times something plus y2 times something else. So what goes in these brackets? So this first one, y1 times, so y1 here, and there's a y1 there. So we get y1 times y2 double prime, y2 double prime, and then plus a of t times y2 prime. So plus a of t times y2 prime. Then this next bracket, we get y2. So where's the y2? There's one there, and then there's one there. So first of all, I put plus here, but let me actually make this negative. Emphasize that because both of these terms are actually negative, so I don't need a plus here. So minus y2 times, so what goes in the first term? That's going to be y1 double prime plus a of t y1 prime. Now look at this. So each of these terms, well, let's do the first one first. This is y2 double prime plus a of t y2 prime. Where have you seen that before? Let's go up to the top and look at that, these first two terms of this ODE. Now y2 is a solution to that ODE. So if you plug y2 into here and you get y2 double prime plus a of t y2 prime, that has to be equal to the negative of this, b of ty. So this is in fact y1 times negative b of t y2. And similarly, this next term is the same thing, it's just with a y1 instead of a y2. This creature here, y1 double prime plus a of t y1 prime, is this thing in the box. This solves the ODE, so if you put ones in the subscript, then that has to equal the negative of this last term. So that's negative b of t y1. And now notice that, well, I'm going to make this minus minus a plus plus. And now we have these two terms. Both of them are y1, y2, and b of t. This one's negative. Here we have y1, y2, and positive b of t. They cancel, and we get 0. So we just verified that the Wronskian does indeed solve this ODE up here. Okay, so now what are we going to do with that? Well, let's solve this ODE. We can separate variables. So we get dw dt equals negative a of t times w. And we can separate variables, put the w's on one side. dw over w equals negative a of t dt. Let's integrate both sides. We get the natural log of w is, well, we get, I guess, nothing really new. The integral of a of t dt. So now let's exponentiate both sides. And now we get the absolute value of w. I'm going to not write the absolute value signs just yet, and we get, well, we really should get a c here at some point. So we get c e to the negative integral of a of t dt, and since we put this constant here, which could be plus or minus, we don't need an absolute value sign up here. So here is our solution to this ODE. That verifies this claim. And now it's easy to see why the Wronskian is either identically zero or never zero. This exponential function, I think I said this earlier. This exponential function, this is positive. It's never zero. So the only way this is ever going to be zero is if c is zero, in which case the whole thing is zero. Otherwise, this is never zero. So that's Abel's theorem. It wasn't as bad as it looked. I mean, it took a few minutes, but hopefully you can see why it's basically just plug and chug, the things that you could have seen in first order or your intro ODEs course, and actually a lot of people did. I don't usually include it because it does involve linear pendants and the Wronskian, but it really is straightforward. Here's an important corollary and technique of Abel's theorem that's called reduction of order. Suppose that we only know one solution, we'll call it y1 of t, of a second order ODE that is linear and homogeneous. Then we can solve for the second solution, let's call it y2, and that satisfies a first order inhomogeneous ODE. y2 prime plus a of t y2 equals g of t, and let me tell you in a moment what a of t and g of t are. I've written it like this so you recognize that it is indeed a first order inhomogeneous equation. So a of t is negative y1 prime over y1, and g of t is the Wronskian divided by y1, which by Abel's theorem above is just e to the minus integral of a of t dt divided by y1. Now I've not included the constant of integration c here because this is a first order ODE, and when we solve it we will get another constant of integration. So this ends up not being necessary, so I've just set it equal to 1. Let's prove this. And once again, I'm saying proof when I really mean just verify. So the Wronskian is this determinant, which is y1 and y1 prime in the first column, and y2 and y2 prime in the second column. And that's y1 times y2 prime minus y1 prime times y2. And I'm going to say this is equal to w, just to call it something. So now, remember, we know what y1 and y2 are. We assume that we have a solution. So let's divide both sides by y1. You see what's going to happen? So the y1 cancels right here. Well, it cancels with that. And let me rewrite this equation right here. And we have y2 prime minus y1 prime over y1, y2 equals w, which is, remember, w is this exponential function. So I'm going to write that as e to the negative integral of a of t dt divided by y1. And that's all we had to do. Now, this technique generalizes easily to higher order equations, though in practice you don't usually deal with more than second order, but if you had an nth order ODE and you knew n minus 1 solutions, you could use this technique to reduce the order of the equation by 1. Let's do an example of this reduction of order technique. So here is an example of a second order homogeneous ODE. So solve y double prime plus 4y prime plus 4y equals 0. Now, if you're watching my lectures in order, this should look familiar because we did this at the very end of the last lecture. So this is one of the ones where there's that double root. So if you haven't done it, I'm going to go through it fairly quickly, meaning if you haven't seen that lecture. So y of t, you assume it's e to the rt. You take a derivative, and that's r e to the rt, and then y double prime equals r squared e to the rt. Now you plug these things back into the ODE. Y double prime, well, what you get is you get an e to the RT in every term, and then you get r squared plus 4r plus 4 equals 0, and you get, well, you divide through by e to the RT, and you get that r plus 2 quantity squared equals 0. So this technique only yields one solution, so that's y1 of t equals e to the minus 2t. So there is your first solution. And unfortunately, we don't get a second one like this. So what did we do last time? Well, there were several ways. One way that you likely know and remember is that you just remember that your second solution is, you just stick a t in front. It's t e to the minus 2t. And if you do remember that, that's fine. You can use it. But if you don't remember that, remember what we did is we said, or we can take y2 of t and assume it's of the form v of t e to the minus 2t and solve for v of t. So here, well, the first solution is 1 times e to the minus 2t. So maybe there's a solution that's a little bit more general, some polynomial times e to the minus 2t. And this will turn out to be any, not just t, but any at plus b will work. And so we just pick the easiest one and let it be t. So here is the third technique that we just learned, reduction of order. So now y2 prime minus y1 prime over y1 times y2 equals the Wronskian over y1, which is e to the negative integral of a of t dt over y1. Now, if you don't have this memorized, that's fine. I don't really have it memorized either. But remember, it's so easy to just rederive it from what the Wronskian actually is. So it's y1, y1 prime, y2, y2 prime. It's the determinant of this matrix. And if you write that out, it's y1, y2 prime minus y1 prime, y2 equals w. There's your ODE right there. I mean, you know y1 and y1 prime. You know w. You can get that from Abel's theorem. And so you just got to solve for y2. So again, if you don't have this memorized, I understand, you don't really need it. So now let's actually plug this thing in. So what do we have here? So we have y2 prime minus y1 prime, that's minus 2 e to the minus 2t, and y1 is e to the minus 2t. Right away, let's just make this minus minus plus plus. And we have y2. And then on the right-hand side, we have e to the negative integral of a of t. What's a of t? That's this. So this is a of t. So that's e to the negative 4t divided by e to the negative 2t. That's what y1 is. So if you simplify this, let's see. So these guys, the e to the negative 2t's are going to cancel, and this e to the negative 4t over e to the negative 2t is e to the negative 2t. So we have y2 prime plus 2y2 equals e to the negative 2t. Now there are multiple ways to solve this equation. You can use integrating factor, you can use variation of parameters, you can use undetermined coefficients. We'll go over these in a couple of lectures, but right now I'll just use integrating factor because this one, in this case, actually is easiest, because you may look at this and this is one of those annoying cases where the forcing term actually solves the homogeneous equation. So using the integrating factor, remember how to do that? So the integrating factor is, you take this term, so the IF for integrating factor is e to the integral of that, so that's e to the 2t. So when you multiply the left and the right hand side by e to the 2t, what you get with the integrating factor method is e to the 2t times y2 prime. If you're rusty on it, that's fine. Again, you have seen it before. You could use Wolfram Alpha or a computer if you wanted to, and we'll review this again in a couple of lectures. So here's the left-hand side, and the right-hand side is the integrating. You have to multiply the integrating factor by both sides of the equation, so that will cancel with e to the 2t and e to the minus 2t, so you get 1. So now if you integrate both sides, I'm going to move up here, so the integral and the derivative goes away, and you get e to the 2t y2 equals, the right-hand side is t, well, it's t plus c, I almost forgot that. You need the c. So now you, oh, actually you don't really need the c, but I'll stay with it. So now let's divide both sides by e to the 2t, or equivalently multiply by e to the minus 2t, and you get y2 equals t e to the minus 2t plus c e to the minus 2t. Now we're just looking for a second solution. That's all we need. So we don't actually need that term. We can set c to be 0, and here is our y2. So now our general solution is we have y1 and y2, so y of t equals c1 e to the minus 2t, that's our y1, plus c2 e to the c2t e to the minus 2t, that is our y2. So there is our final solution, and so that's the same thing that we got at the end of last lecture. Might be a little bit long, so in this case it's maybe not necessary, but there will be cases, we'll see with Bessel's equation at the very end of this series of lectures, and others when we absolutely need something like this. And again, this thing works for not just second order, but nth order ODEs. Let's conclude with two more examples of applications of Abel's theorem. So here I've put the statement of Abel's theorem above just so you can see it. So here's an example. I think I mentioned this in the beginning of this lecture. So let's compute the Wronskian of these two functions. y1 of t is sine of 2t, and y2 of t equals sine t cosine t. Now this is the sort of thing where you look at this and you think, well, these are not scalar multiples of each other, so they're linearly independent. But this is one of those trick ones because recall the trig identity that sine of 2t equals 2 sine of t cosine of t. So these two functions are clearly not independent, linearly independent, because if I take one of these and negative 2 of these, then I get 0. So for example, y1 of t plus negative 2 y2 of t is going to equal sine of 2t minus 2 sine of t cosine of t, which equals 0. So let's compute the Wronskian of this, see what happens. So w equals sine of 2t, now let's take a derivative, and we get 2 cosine of 2t, and then we get sine of t cosine of t. Now we need the product rule for this, so we get, let's see, so the derivative of this is cosine of t cosine of t, so that's cosine squared of t, and then what do we get? We get sine of t times the derivative of cosine, so that's minus sine squared of t. So we look at this and, well, the Wronskian, let's actually compute this determinant. So this is sine of 2t times these guys, sine of 2t times cosine squared of t minus sine of 2t times sine squared of t, and then minus 2 sine of t cosine of t cosine of 2t. So now it is not at all clear that this thing is going to be 0. And it should be 0. Now, of course, you could do trig identities to this, but in that case, you could have done trig identities to this original thing as well. So, well, let's see what we can determine. So remember that the Wronskian is either identically 0 or it's never 0 on any fixed interval. So let's just see what happens if we actually plug in 0. So let's go here and let's plug in t. I'm just going to pick 0. Maybe that's not the right thing. Let's see what happens. Plug in 0, and well, this term is 0 minus Any sort of sign in here is going to be 0. So sine of 0, or sine of 0 and sine of 0. So all of these terms are 0. So the Wronskian of this is 0. Now, what does that tell us? That it actually doesn't tell us that these things are linearly dependent. Remember that if the Wronskian is non-zero, then the functions are linearly independent, but the converse fails. So, well, from Abel's theorem, we know that the Wronskian is either identically 0 or never 0. And here it's 0 at some point, which means it has to be identically 0 at every point. So even if we plug in some irrational number in for t, this thing is always going to be equal to 0. Again, we have to be careful. That does not mean that we can conclude that these functions are linearly dependent. But I will say this, it gives very good evidence that they are. Remember, the simplest example of two functions whose Wronskian was 0 that were not linearly independent were y1 was x squared and y2 was absolute value of x times x. So this is not a simple example. I mean, this is a little bit contrived because, again, the first of these look like that. Let's go through the origin, and the next one of these look like that and that. So this doesn't tell us that these are linearly dependent, but it should put our guards up. It should say something's going on here. It's very likely these things are linearly dependent. And in fact, when you check the trig identities and you get that red flag, you check these things and you should be able to verify that, yes, these things are linearly dependent. But it does not follow from the fact that the Wronskian is equal to 0, which in this case means identically 0 from Abel's theorem. Here's our last example of a result that we can derive from Abel's theorem. So I claim that there is no ordinary differential equation of the following form, in other words, second order linear and homogeneous, that has both t squared and t plus 1 as solutions. It's not at all clear why this should be the case. It seems like potentially given two solutions, maybe we could cook up such an ODE, but I claim that it's impossible. And here's why. So let's compute the Wronskian first. So y1 in the upper left corner, that's t squared. Its derivative is 2t. y2 is t plus 1, and its derivative is 1. So let's the Wronskian here, so t squared times 1, that's t squared. And then we are subtracting 2t times t and 2t times 1. So that's t squared minus 2t squared minus 2t. And so this is minus t squared minus 2t. Is that correct? Yes, so this is minus, let's see, so let me actually remove that. So it's, I'm going to factor out a t minus t times t minus 2, or t, I should say t plus 2. Is that correct? Yes. So this is, so the Wronskian has roots at, so the roots of this are t equals 0 and t equals negative 2. Now what's the problem? The Wronskian is either identically 0 or it's never 0 on any fixed interval. And this equation, if it has both these things as solutions, it's going to be defined everywhere. But so let's take an interval that contains either 0 or either negative 2, and, well, what do we get? We get something that's impossible. The Wronskian is either, again, identically 0 or never 0. Here, this Wronskian is 0 at 2 points. That's impossible. Therefore, there cannot be an ODE of this form that has both of these things as solutions.